So students, in this problem, a magnet is hung horizontally in a magnetic meridian by a wire without any twist. So it remains in the magnetic meridian. If the supporting wire is given a twist 180 degree, suppose this wire is the top and we are giving twist, suppose like this. અહીંયા દોરી બાંધેલી છે, નીચે magnet છે, તો પહેલા આમ ગોઠવાયેલો છે. હું આને twist 180 degree નો આપું છું. તો આ જો magnet ન હોત તો એ ધીમે ધીમે એ પણ ફરીને 180 આવી જાય. પણ this is magnet. તો શું કરે છે એ? The magnet rotates 30 degree. એટલે 180 degree rotate થવું એમ કેટલું થયું 30 degree. It means twist is 150 degree in the wire. Okay. Now if magnet is used, then the twist is 270 degree at the supporting end of the wire also produce the same 30 degree. Compare the magnetic dipole. So torque on magnet, torque is equal to mb sin theta. Okay. This is torque 1 for magnet 1. Magnetic field, that is original component of magnetic field, so I write B only, sin theta. This is balanced by the twist in the string, so is equal to k phi. Theta is the angle made by the magnet with the magnetic field, that is 30 degree, and phi is the twist in the wire, that is 180 minus 30. So here theta is equal to 30 degree and phi is equal to 180 minus 30 degree is equal to 150 degree. Okay. Torque on magnet 1. And for 2 I can write, for magnet 2, m2b sin theta is equal to k phi 2. Okay. K is constant because wire we are not changing. અહીંયા theta भी same આપ્યા છે 30 degree, maybe different, તો બી આન્સર તો આવી જ જવાનું હોય. So we take ratio of this 2. Okay, what is phi 2? So phi 2 is equal to 270 minus 30 is 240 degree. Okay, and theta is equal to 30 degree. એ જુદું હોય તો બી આન્સર તો આવી શકે. We don't need extra data also. This is 1 and this is 2. I take the ratio. So we get m1b sin theta upon m2b sin theta is equal to k phi 1 upon k phi 2. And therefore m1 upon m2, this is cancelled. Same theta kiddu to bhi answer avi jaye mitro, is equal to k is cancel out. So phi 1 is 180 degree, sorry 150 degree, and phi 2 is 240. So 3 phi's are and 3 8's are. 3 phi's are and 3 8's are. So phi by 8 is the ratio of their magnetic moment. Okay. It is given in magnetic meridian. એટલે અમારે જે કઈ twist છે એટલે 30 degree થશે. Okay. Next one, a magnetic needle is hung by an untwisted wire so that it can rotate freely in the magnetic meridian. They use often word magnetic means it remains parallel to the magnetic meridian. It can rotate like this in vertical plane. In order to keep it in a horizontal position, a weight is 0.1 gram is kept on one pole end of the. Okay, so our aim is to find out the value of the vertical component of Earth magnetic field. So here Earth magnetic field હશે નીચેની તરફ, એને હું BV કહી દઉં. અહીંયા બી BV પર સાઉથ છે એટલે ફોર્સ ઉપર લાગશે. This is BV, but force on S, this is force, downward force લાગશે એને FN. And we are putting one weight. It is already here. I shown. You already shown the text. So this is, we put the mass here. So નીચે આવતું રહેશે mg. તો તમે જો this is one force, that is Fs, and this is Fn. Force is equal to pole strength into magnetic field, અને આ mg છે એને કારણે નીચે આવશે. તો we have three forces, Fs and Fn rotates magnetic needle, means मतलब magnetic needle in clockwise direction. Okay, and mg rotates in anti-clockwise direction. So આનું torque ને આનું torque add થશે, આનું ઓપોઝ થશે. So we take this positive torque and this is negative torque. આપણે યાદ કરો રોટેશનલ મોશનમાં આવું કરીએ છીએ. So torque 1 plus torque 2 is because of the north pole, because of the south pole, plus torque because of the mg is equal to 0. So torque north is equal to, we know, force into distance. So PBV into distance is L. Again, PBV distance is L, and this is minus mgl equal to 0. So we can calculate what is the vertical component. So BV we can calculate, this is 2 times. Okay, LL will cancel out. So mg I2, m is equal to 0.1 into 10 raised to minus 3. G is 9.8 divided by 2. So this comes out to be 4.9 into 10 raised to minus 4 Tesla. Okay, isn't it? 4.9. So this is the magnetic field, vertical component or magnetic field. Doubt લાગે છે એટલું વધારે ફીલ આવે છે. ઓ અહીંયા p ભૂલાઈ ગયો છે. P is there. P, what is P? That is 10. Oh, now is okay. કારણ કે point, it should be less than this one, 10 times over. So this is 4.9 into 10 raised to minus 5 Tesla. Now it is correct. Now it is correct. સમજમાં આવ્યું? મને કેમ ખબર પડી ગઈ કે 0.36 ગોસની આસપાસ છે, તો આ તો વધી ગયું હતું, 4.9 ગોસ થઈ ગયું હતું, એવું હોય નહીં. So I try to find the mistake. Next, as shown in the figure, plane PSTU alpha and plane PSVW. So these are the two planes like that. આવી રીતે બે પ્લેન છે, બંને વચ્ચેનો એંગલ કેટલું છે કે 90 છે. એની વચ્ચે કોણ છે? મેગ્નેટિક મેરિડિયન છે. ધ્યાન રાખજો, this is magnetic meridian, this is magnetic meridian, right hand. આ એંગલ જે આપ્યો છે 90 માઇનસ આલ્ફા આપ્યો છે, અને આ એંગલ આપ્યો છે આલ્ફા, like this is alpha, this is 90 minus alpha. So if you perform the experiment to calculate, also to find the deep angle, તો આ જે પ્લેન છે, પહેલી પ્લેન is PSTU, તો એમાં deep angle કેટલો મળે છે? 5.1. અને જો એક્સપેરિમેન્ટ અહીંયા કરું તો એ મળે છે 5.2. So what is the 2 is 5, તો એની વચ્ચેનું રિલેશન આપણે આવું લાવવાનું છે. તો જો હું એક્સપેરિમેન્ટ ગ્રીનમાં કરે તો મને આન્સર, અહીંયા નીડલ હું રાખે આવી રીતે, નીડલ હું અહીંયા રાખે તો નીડલ મારી એટલી નમી જાય. ઓકે, પણ હું રાખું છું. તો if experiment is performed in this magnetic meridian, તો અહીંયા આગળ જો નીડલ આમ થાય તો this is my phi. પણ એક્સપેરિમેન્ટ અહીંયા પરફોર્મ કર્યો છે બીજી પ્લેનની અંદર, નીડલને અહીંયા રાખીને આમ, તો નીડલ નમી જાય. So this angle is phi 1, અને જો અહીંયા આગળ પાછળના ભાગની જે પ્લેન છે then it is phi 2. Okay, so we have to assert the relation between these two. So we know that deep angle for that tan phi is equal to BV upon BH. That is known. So this is BV vertical component. I am performing experiment here, this one. So this is BV. If it is performing magnetic variant, this is BH. પણ આ BH એટલે BH ની બાજુમાં છે. So instead of BH, in our case, it is BV upon BH prime. Because we are not performing experiment in the magnetic variant, we are performing experiment in the plane which makes angle alpha. So BH prime and BH both are related with this relation BH cos phi. Here is the BH, but here is the BH prime. Angle is alpha, so near side is BH cos alpha. So is equal to tan phi upon cos alpha. Understood? This is phi 1. This is phi 1 for in this plane. For which plane? Okay, P as TV. P as TV. Apparent, it is called apparent dip. Apparent dip angle equal to phi 1. So we can write this. Let us say this is 1. And if we take another plane, that is P as VW, apparent dip angle is equal to phi 2. So tan phi 2 equal to BV upon BH cos 90 minus alpha. Now angle is 90 minus alpha. So it becomes BV upon BH sin alpha. So it is tan phi upon sin alpha. So this is tan phi. I say this is 2. This is important formula, yaad rakjo. If you perform the experiment other than the magnetic meridian, dip is phi 1, the real dip is phi, this is the relation. Okay, I asked one question in your question of the day also. હવે મારે શું કરવાનું છે? I want to show cot square અને તો મારે આલ્ફાનું એલિમિનેશન કરવાનું છે. I have to eliminate I. તો હું શું કરું? From 1 and 2, I write cos square alpha is equal to what? Tan square phi upon tan square phi 1. Okay, from 1. And from 2, sin square alpha is equal to શું થઈ જશે? Tan square phi upon tan square phi 2. So this is 3 and this is 4. So now add this. So by adding 1 and 2, we get 1 is equal to, 1 થઈ જશે left side one. So we get tan square phi upon tan square phi 1 plus tan square phi upon tan square phi 2. We take tan common, other side become denominator, so it becomes cot square phi is equal to this 1 upon cot tan square phi 1 plus cot square phi 2. So this is very important relation. Phi 1 is the apparent dip with angle alpha, phi 2 is apparent dip with angle 90 minus alpha with the magnetic meridian, phi is the true dip. So આ તમારે એક યાદ રાખવાની છે formula. Okay, thank you very much. So welcome students in this exemplar problems. We are going to solve exemplar problems. A toroid of n turns mean radius r and cross sectional radius is r. A carries current I. It is placed on a horizontal table taken as a xy plane. Its magnetic moment so is non-zero and points in the z direction. So this is our toroid, suppose, and this is xy plane. So this is x and this is y. So we know in the toroid there is a winding, okay, and current is flowing through the winding. So we have magnetic field, and this magnetic field is in circular shape like this. Depending on the current direction, there is a direction of magnetic field, okay, clockwise or anti-clockwise. So here each turn has magnetic moment, and if you do vectorially, so it is 0. So it doesn't have any magnetic moment resultant. So I think this option is 0. Otherwise, there would be a field falling as 1 upon r cube at large distance outside the toroid. So here outside the magnetic field હોતું જ નથી અમે જે. So this is C option is correct one. The magnetic field of Earth can be modeled by that of a point dipole placed at the center of the Earth. The dipole axis makes an angle, so this is our Earth and this is our north and south. And magnet dipole is like this. This is geographic north and geographic south, huh? And this is magnetic north and magnetic south. And you must be knowing where toward the magnetic south we have magnets north, here north and here south. So the field lines are coming out. And this angle is there. Okay, the 11.3 degree. Declination is nearly 0 at Mumbai. Okay, the declination varies between 11.3 west to 11.3 east. So it is the correct one. So it varies. Judi ketlu 11.3 west to 11.3 east. So this is the correct option. List 0. Declination is 0. Okay. The plane defined by dipole axis. The plane defined by dipole axis and axis passes through Greenwich. This is geography. Declination average over Earth must be always negative. That is, so this is the correct one. So in permanent magnet at room temperature, the magnetic moment of each molecule is 0. No, 0 na જ હોય. Paramagnetic and ferromagnetic ને magnetic moment હોય particles ને. Diamagnetic ને ના હોય. And we know that permanent magnets are made from the ferromagnetic material. Ferromagnetic material has domain structure. Domain means some particles group of some particle in one direction, like this. This is ferromagnetic. But if it is permanent magnet, this all domains are aligned in direction. So we get one domain structure. So you can say that domains are perfectly aligned. બીજા વર્ડમાં તમે એમ કહેશો બધા પાર્ટિકલ ડોમેઇન અલાઇન થવાને કારણે થાય તો છે જ, થોડું ઇમ્બિગ્યુટીસ લાગે, પણ પાર્ટિકલ બી અલાઇન તો થવાના છે, પણ this is because the domains are aligned. Okay, so D is the correct one. Consider the two idealized system, a parallel plate capacitor with large plate and small separation and a long solenoid of length. L is very good canal, it is cross-sectional. In one, E is ideally treated as a constant between plate and 0 outside. In magnetic field, is constant inside the solenoid, 0 outside. These idealized assumptions, however, contradict fundamental laws as below. So we have Gauss law E dot dA for closed surface is equal to sigma q upon epsilon naught. And if we take B dot dl, B dot dA, then it must be 0. Okay. So for electric field, these are not in closed nature. and so this first is okay, but for second one, if it is straight line, then this law is wrong, because magnetic field lines are always closed loop. If they are closed loop, then and then you get integration of B dot D equal to 0. So this contradict in second case. Okay. A paramagnetic sample shows a net magnetization of 8 ampere per meter when placed in an external magnetic field of 0.6 Tesla at a room temperature 4K. When the same sample is placed in external magnetic field 0.2 T at temperature 16, the magnetization will be. So we know that magnetization is equal to or proportional to B and inversely proportional to T. So we can say that M2 upon M1 is equal to B2 upon T2 into T1 upon B1. And therefore M2 is equal to what is B2? So it's 0.2 Tesla, temperature is 16 into T1 is 4 and V1 is 0.6 into M1 and M1 is 8. So if you simplify 8, so I think 4 jar, this is 4 2 jar, okay, so 2 2 jar 4, 0.4 upon 0.6, so I think it is 2 by 3 ampere per meter. So this is the option B is the correct one. So now onward, more than one options are correct. So S is the surface of a lump of material, magnetic material. Suppose this is our magnetic material. The line of B are necessarily continuous across C. So whatever the number of lines inside the material, it should be completed. Okay, so B must be continuous, that is the thing. Some lines of B must discontinuous, so it wrong થઈ ગયું. Line of H are necessarily continuous across C, S. So H એટલે શું છે? Okay, B is equal to mu 0 H. So H is equal to B upon mu 0 outside, and inside H is equal to B upon mu 0 into mu R. Outside B upon mu 0, inside B upon mu 0 mu R. So outside the H and inside the H are different. So naturally some lines are discontinuous. So option D is also correct. H depends on permeability. B permeability પણ lines are always continuous. એટલે તમારે અહીંયા આગળ continuous રહેશે અને અહીંયા આગળ બદલાઈ જશે. Okay. The primary origin of magnetism line in atomic current, Pauli exclusion principle, polar nature of molecule, intrinsic spin of electron. For any origin, so why we get magnetic field? So because of motion of the charged particle. So when electrons are revolves around the nucleus, it is one type of current only. So we get the magnetic field. So A is the correct one. Pauli exclusion principle, that is totally different. Two electrons cannot have same energy like that. Polar nature, not because of that also, because we need motion, intrinsic spin of the electron. So of course because of this also. So these both are motion, orbital motion and intrinsic spin of electrons are responsible for origin of magnetism. A long solenoid has 1000 tons per meter, carries a current of 1 ampere. It has soft iron core of mu r is 1000. The core is heated beyond the Curie temperature. So you know that at Curie temperature, material converts into paramagnetic. Ferromagnetic is converted into paramagnetic. That is called Curie temperature. The H field in the solenoid is unchanged. Yes, because H is equal to Ni. N is the number of turns per unit length, is the external current flowing. So these are not things, so H remains unchanged, but B will change because B is equal to mu H. So this will change. So So mu will decrease, and therefore B is also decreases. The H and B field in the solenoid are unchanged, that is magnetizing the core reverse no. The magnetization in the core diminished by a factor of about 10 plus to 8. So we know that susceptibility of a paramagnetic and susceptibility of ferromagnetic is quite different, very less for paramagnetic compared to the ferromagnetic. So it will change. This both are the correct one. Essential difference between electrostatic shielding by conducting shell and the magnetostatic shielding is due to the electrostatic field lines can end on charge and conductors have free charges. Lines of B can also end by conductors cannot end them. Electrostatic field lines can end on charges and inductors have free, what is this? Electrostatic field lines can end on charges and conductors have free charges and conductors have free charges. Okay. Lines of B can also end, but conductors cannot end them. Line of B cannot end on any material and perfect shielding is not possible. Shells of high permeability material can be used to divert line of B from interior region. This is, I think, suppose you have material like hollow and if you apply the field, so it will go like this. So this is not affected. So D is the right one. One thing is sure. One option D is correct according to my. Again, I read it. Electrostatic field lines can end on charges and conductors have free charges. तो field line अंदर पास न થાય કારણ કે ત્યાં end થઈ જાય છે. આ બી અચ્છા સાચું હોઈ શકે. Lines of B can also end but conductors cannot end them. No, the conduct end જ નથી થતું. Line of B cannot end on any material and perfect shielding is not possible. Lines of B perfect shielding અહીંયા possible બને છે. Yes, this is now again I read this. Line of B cannot end on any material. Suppose we have this material and there is some cavity, magnetic field is coming. So if this is not very high, then some line may leak there. So it may possible. So 100% shielding is not possible. And તો મારે જોતું હોય તો બહુ હાઈલી પરમિએબલ તો આમાંથી એક પણ લાઈન આમાંથી પાસ થાય નહીં. એટલે આ બી કરેક્ટ છે ACD. Okay. Let the magnetic field on the earth be modeled by that of a point magnetic dipole at the center of the earth. The angle of dip at a point on the geographical equator is always 0. Can be 0 at specific point. Can be positive or negative is always 0. No, 0 possible nothing. Can be 0 at a specific, maybe 0. So તમે આવું જ છે કે suppose this is our earth and this is geographic equator and this is magnetic equator and pole is here. So 0 તો ન થાય. Can be 0 at specific. Yes, it is possible. It is always 0 wrong છે. Can be possible 0. Yes, possible છે. અહીંયા આગળ આજે this is geographic equator and this is the magnetic equator. તો અહીંયા એ 0 હોઈ શકે અને જો હું અહીંયા આગળ જતો રહું તો geographic equator below તો એની direction અહીંયાની direction બી ઉલટી હોવી જોઈએ. So this side is positive, this side negative. So it varies from positive value to negative value. So it may be positive or negative. Yes, it is true. This is true. And it is bounded. ગમે તેટલી ના હોય. So it is also true. Okay. A proton has spin and magnetic moment just like an electron. Why then its effect is neglected in the magnetism of the material? So in theory part we have discussed magneton. Bohr magneton is EH upon 4 pi m. If for electron it is the electron. And if it proton, so magneton you can say inversely proportional to mass. So electron is the mass electron level and it is a proton, then I have to take the mass of the proton because charge is same. So this Bohr magneton is very less for the proton compared to the electron, since mass of the proton is around 1800 times larger. So this is not considered in the magnetism. Okay. So permanent magnet આપેલું છે. This is the intensity of magnetization. So that is the M total upon volume. This is known. M total એટલે શું થાય? Total number of turns into area into current. This is the magnetizing current. Volume is area into length. Area is cancelled. Okay, and this NIM, this is the magnetizing current. This is equal to MI. M is 10 to 6 ampere per meter into 10 centimeters, so 0.1. So it comes out to be 10 to 5 ampere. So this is the total current. It looks like this much current is flowing. Okay. So a ball of magnet superconductor material is dipped in a liquid nitrogen and placed near the bar magnet. In which direction will it move? So when it is dipped in liquid nitrogen, it converts into superconductor. Superconductors are diamagnetic. So when it is placed near bar magnet, the magnetic moment is induced in such a way that it opposes the magnetic external field. તો જો આ બાજુ એ મેગ્નેટિક મોમેન્ટ છે કે સાઉથ ટુ નોર્થ એટલે આ બાજુ, તો આ બાજુ ઇન્ડ્યુસ થશે એકોર્ડિંગ ટુ લેન્ઝ લો. તો એનો ઓપોઝ કરે શું થશે? દૂર જશે. ઇટ મૂવ ટુવર્ડ ધ લેફ્ટ. ઓકે, ઇટ વિલ મૂવ ટુવર્ડ ધ લેફ્ટ. એન્ડ મેગ્નેટિક મોમેન્ટ કઈ બાજુ ઇન્ડ્યુસ થશે? જે ફીલ આપો છે એની ઓપોઝિટમાં. અહીંયા મેગ્નેટિક મોમેન્ટ આમ છે તો આની મેગ્નેટિક ઓપોઝિટ આવશે. ઓકે. And next one,